Welcome to today's lecture on battery material substitution. In this section, we will explore how emerging battery chemistries are reshaping material demand, particularly through the substitution of critical elements. In this section, we will examine critical materials used in alternative battery chemistries by addressing three central questions. Which materials are being substituted as we move away from traditional lithium-ion batteries? Which critical materials are no longer required in alternative chemistries? Which new materials are becoming essential for next-generation batteries? These questions provide a framework to understand how battery innovation impacts global resource needs. By 2050, lithium iron phosphate batteries are projected to dominate the global battery market, as shown in this figure. This shift is driven not only by better material availability, but also by improvements in performance and cost effectiveness. Compared to nickel, cobalt, and manganese technologies, LFP batteries offer several material-related advantages, notably a reduced reliance on critical materials such as nickel and cobalt, which are constrained by supply chain risks and environmental concerns. However, LFP batteries rely heavily on phosphorus, a relatively abundant element, but one that is so vital for agriculture, raising new concerns about cross-sector competition for this resource. As the adoption of LFP batteries expands, especially in the electric vehicle sector, the demand for phosphorus is projected to rise sharply. This figure illustrates that phosphorus demand could increase by 36 to 40 times between 2020 and 2050, driven by the growing global EV fleet. A major concern is that by 2050, phosphorus demand may outpace global production capacity. Since phosphorus is also a key nutrient in fertilizer, this trend could lead to significant tensions between energy and agricultural sectors. This slide shows that lithium-sulfur and lithium-air batteries could together account for up to 60% of the battery market by 2050, making them major alternatives to today's mainstream chemistries. Compared to MCM technology, several shifts in material demand are expected. Nickel and cobalt demand may stabilize or decline after 2030 due to reduced use in these newer chemistries. However, lithium demand will increase significantly as both lithium-sulfur and lithium-air batteries use lithium not only in the cathode but also in the anode. This expanded use of lithium is a key contributor to the higher energy density and performance of these technologies, but also poses challenges. Managing lithium supply sustainably will be crucial to avoid future bottlenecks. To summarize, this lecture examined how battery material substitution affects future material demand. Alternative chemistries such as LFP, lithium-sulfur, and lithium-air reduce dependence on nickel and cobalt. The rise of LFP batteries may increase phosphorus demand up to 40-fold by 2050, creating competition with agriculture. Lithium-sulfur and lithium-air batteries require significantly more lithium, presenting new supply challenges. Understanding these trends is key for planning sustainable, resilient battery supply chains in the coming decades.